We're looking at the Swarm satellite pass checking program. We've entered in our location and going to take a look at the information it gives us. It gives us a graphic here that is showing dates on the left-hand side here, and what's on the horizontal axis are times. They're not displayed here. We have to select one of these little blue rectangles to get the times, but you can see that we've got basically 5 windows here of time during which there are satellite passes. Each little blue block represents one or more satellites passing over us, visible here at Stanton, at least above the horizon. And the darker blue the rectangle is, the greater the maximum elevation of the satellite during its pass. So this blue block right here, we select it, gives us a pass that has a maximum elevation of 82 degrees, which is pretty good, pretty high in the sky. 90 degrees, of course, being the maximum. And we also find out that it's a pass of duration of almost 38 minutes. And so we have basically 5 windows each day during which there are satellite passes, corresponding to 5 different orbits, each containing numerous satellites positioned at various lines of longitude around the Earth at any given time. Of course, their orbit is fixed. It's a low Earth orbit. It's a fixed orbit, and the Earth rotates underneath that orbit, so that just about every place on the planet is visible to the satellites at some time during the day. So we're going to be dealing with satellite passes in this 4th window, which is a pretty wide window, and roughly from 2 p.m. to 4:30 p.m. Currently, and we're going to be checking for reception of satellite signals using a short antenna, the quarter wavelength antenna that you saw at the opening of this video, and a longer 5/8 wavelength antenna. The wavelength we're talking about here is 2 meters, and so roughly 150 megahertz, and that's where our satellite communication occurs. So we'll get started on that and take a look at what we're getting from the satellites using the short antenna first. So we're connected to the Swarm Eval Kit satellite transceiver via Telnet using PuTTY, and we're receiving a steady stream of reports from the satellite modem that's inside that transceiver. We've got reports on background noise. These report like this one right here that gives us negative 93 dBm, that's decibels over a milliwatt, reading for the noise level. We're getting date time stamps, the reports like this with $DT. It's a year, a month, a date, an hour, a minute, and a second. We are getting latitude and longitude being reported based on GPS receivers reading, and so on. But what we're really interested in is the one report that we're not seeing yet here, that is the report that we get when the satellite transceiver actually hears a satellite beacon. The satellites are constantly transmitting beacons, and when it does hear a satellite beacon, it's going to give us some information about that satellite. And we're going to take a look at the sort of information that we get from the satellite next here. we're going to take a look at some data that we received from the satellite, from satellites a few days ago here. This is what the satellite beacon report looks like. It gives us the RSSI, the relative signal strength indicator for the satellite signal. So that's in dBm, decibels over a milliwatt also. We get a signal to noise ratio report. We get a frequency deviation from the actual transmit frequency due to the movement, the Doppler effect of the movement of the satellite. We get a date and time, and we get an ID of the satellite. The DI is a device ID for the satellite, which is a hexadecimal value. This value at the end is a checksum, and the $RT is just an indication that this is a report of a satellite transmission. So what I did was just to write a little Python program that would take open up the log file produced by PuTTY of all of every single one of the reports and extract these RT, these reports of satellite transmissions from it. And here you can see that during that 4.5 hour window, many different satellites were heard. A given satellite might be heard multiple times, like right here, the very first, the same satellite produced 2 beacon transmissions. And down here we've got a whole bunch of transmissions from this satellite. Lots of transmissions. With this data extracted by the Python program from the whole log file, I just went through and for each satellite I identified its strongest transmission during that 4.5 hour period, with the highest value for its signal report, and put that into an Excel spreadsheet that we'll look at eventually here. And for the purposes of being able to sort all of the reports by satellite ID, and then also perform statistical tests, a t-test on matched pair t-test on the signal report. So we're going to match up the same satellite on using a small antenna, a shorter 1/4 wavelength antenna on one day, and then same satellite. Hopefully we can find the same satellite on a second day using the longer antenna, and then compare those matched pairs of the same satellite, short antenna, and long antenna. And that's the goal of this study, to make the null hypothesis that there's no difference between the antennas, and then see if there actually is a difference and which way it goes. Now there's some controversy here. Actually, there are people, the people who maintain against the standard view that actually a 5/8 wave antenna is poorer in performance than a 1/4 wavelength antenna. Based on some antenna simulations, the claim has been made that unless the antenna is over a large, perfectly reflective ground plane, then the quarter wave is going to outperform the 5/8 wavelength. On the other hand, there are typically people who have used both the 5/8 wave and the quarter wavelength antenna for ham radio communications, who claim that the 5/8 wavelength antenna is better, and the manufacturers of that antenna say that it's better, that it gives a couple dB gain over the quarter wavelength antenna. So we shall see, for our purposes, which, if either of those claims is correct. So here are the results from using the short antenna during the 4.5 hour pass of swarm satellites on February 22nd. These are abstracted from the log of transmissions of the swarm satellite to my PC here over the Wi-Fi network that the swarm satellite transceiver generates. And what I did was to go through the reports of the satellite beacons and pick out the strongest signal for each satellite on that day. And so we had 23 distinct satellites passing overhead and multiple beacons from many of them. And what we have here is the strongest beacon, or the beacon with the strongest signal report given by our satellite transceiver on that day. On the next day, we used the long antenna during the same 4.5 hour satellite pass window and received signals from 26 different satellites. So 3 satellites that were not heard by the short antenna were heard by the longer antenna. And we have the corresponding maximum highest signal report for each of those satellites during that 4.5 hour window. Here we combined the data for the 2 days, the long antenna and the short antenna, and then sorted so that all of the pairs of satellites would show up, the matched pairs that we're going to do a statistical test on as a long antenna for this particular satellite and a short antenna for that same satellite, and so on for all of the satellites that were heard. And in fact, every one of the satellites heard with a short antenna was also heard with the long antenna, plus 3 more satellites that weren't heard by the short antenna. But we're only pairing up the ones that were heard by both for our statistical test. And we did a t-test on both the satellite signal strength and on the signal-to-noise ratio. And the null hypothesis being that there's no difference between the 2 antennas, that the hypothesized mean difference is 0. And what we wound up with was doing a test at the 0.05% significance level. We got a p-value of 0.0003 approximately. So that's like 3/10,000ths. Okay, and so we can definitely reject the null hypothesis that these are the same. And if we look at the means, we can see that we've got about a 5 dB gain for the 5/8 wavelength antenna over the quarter wavelength antenna, which is right about the gain that the manufacturer suggests that the device would have. Something similar with the signal-to-noise ratio. We also can reject the null hypothesis there. Let's see. Need to get down to where we can see the p-value is larger, but still way underneath 0.05. So also we can reject the idea that while the 5/8 wave antenna picks up the signal stronger, it also picks up the noise stronger, so that they basically cancel out. But no, it does give us also a higher signal-to-noise ratio. And so those are the conclusions from the most recent phase of this Swarm Eval Kit project.